All right, welcome everyone. So today we're going to get started. We're going to continue on with what we left off with last time. And where we left off, we were looking at all of our elementary forms. And we're going to go through today, and we're basically going to prove all of these results, or see how to do it, just off of really three kind of basic, really basic derivative rules. And the three that we're going to need are the one for sine, so knowing that the derivative of sine is cosine, knowing that the derivative of cosine is negative sine, and then knowing that the derivative of e to the x is e to the x. And we're basically going to be able to prove all of the other derivative rules here using just those three results. And so last time we had looked at the derivative of tangent. We did the quotient rule to show that the derivative of tangent was secant squared. Today, we're going to continue on with showing that the derivative of secant x is equal to secant x times tan x. And we do have to remember a few things, and that's, we have to remember some trig identities, really. So how is secant? How is tan? How are those other trig functions defined in terms of sine and cosine? And so for secant x, secant is the reciprocal. It's 1 over cosine of x. And so that's what we're going to use to show this result. So we're interested in the derivative of secant x. And the first thing we want to do is just rewrite secant x in terms of cosine. So it's 1 over cosine x. And we're going to do the derivative of that. So we're going to do the derivative of 1 over cosine x. And when we look at that, it's a fraction. So we could use the quotient rule. But there's no variable on the top. There's no variable in the numerator. So the only variable that we see is in the denominator of the fraction. So another way to handle fractions like this, where the variable is only in the denominator, is to rewrite it with a negative exponent. And that's what we're going to do. We're going to rewrite this expression with a negative exponent. That's one of our standard little techniques for dealing with some fractions. Rewrite it as a negative exponent, and then you can just use the power rule. So if we do that here, we could rewrite this as cosine x all raised to the negative 1 power. And we're going to differentiate that expression. Now, just be careful when we're using negative exponents with trig functions. So we just want to make sure we distinguish that this minus 1, it's not the inverse cosine function. That's just an exponent. That's just a power function. So we just want to be careful when we do use negative exponents with trig functions. So I'm going to leave that as cosine x inside the parentheses, and then all raised to the minus 1 power, just to help me remember that we're not talking about the inverse cosine function. That's something very different. All right, so now we're in a position where we can differentiate that with just the general power rule. So what the general power rule says is we can bring down that exponent, the negative 1. So bring it down, put it in front. Keep what you have inside the parentheses exactly the same, so cosine x. And then subtract 1 from the exponent. So that'll take us down to negative 2. And then we take the term that's inside the parentheses, the cosine x, and we multiply by its derivative. So that's just the general power rule. Differentiate the power function part, and then multiply by the derivative of what's inside the parentheses. All right, so now let's calculate that remaining derivative. Derivative of cosine is negative sine. So negative sine x there at the end. And let's simplify that down a little bit. So we have a -1 in front. We have a negative on the sign. So those are just constant multiples. So let's combine those into a double negative, and it just becomes a positive term. And then also that cosine x raised to the -2 power, let's rewrite it so it's not a negative exponent anymore. So we can rewrite that as 1 over cosine x squared. And then we have our times sine x. And then the two negatives just canceled out. Double negative becomes positive. So we did the general power rule, and then we rewrote that negative exponent so that it's back into a fraction. So we're done differentiating, but it's not in the format that we're used to here. It's not secant times tan. So how can we get it there? Well, we can use more of our trig identities. So we're going to break that 1 over cosine x squared term, we'll break that apart into two separate fractions. So we'll write it as 1 over cosine x times 1 over cosine x. And then we have our sine, so times sine of x. So we have, when we have 1 over cosine x squared, that's the same thing as 1 over cosine times 1 over cosine. And what we'll do next is we'll group these terms here into one fraction. So we'll move the sine into the numerator for that second fraction. So we'll have 1 over cosine x times sine x over cosine x. And now if we look at our trig identities, sine x over cosine x becomes tangent. So this is going to become tangent x. And then 1 over cosine x is going to become our secant. So using those trig identities, we get secant x times tan x. So knowing the derivative of secant, it's helpful still just to have it memorized, but we can prove it using our product rule, quotient rule, or chain rule. So just like we did last time for tangent, we could use quotient rule to show what the derivative of tangent is. All right, so for just our basic trig derivatives, this works. But now what about our inverse trig functions? Well, this is where we're going to use implicit differentiation. So what we talked about last time on Tuesday, we're going to use implicit differentiation to show how to calculate the derivative for all of those inverse functions. So first, let's just look at what the definition of an inverse function is. So this is where we use that -1 notation, and we read it as, f inverse. So the function f inverse is the inverse function of f, and the way we define it is that y equal to the inverse function of f evaluated at x is the same thing as x equal to f of y. So it's helpful to think of the inverse function as really in terms of the two cancellation properties that go with it. So we'll look at the first one there. So let x be a number in the domain of our function f. And what the inverse function really does is it just undoes what function f does. So let's see how this looks in sort of our normal composition of functions diagram. So let's say we start with input x. And the way this composition reads, let's plug that into function f. And what function f does is it changes that input and it gives you something out, which we call f of x. Gives you something new out, which we call f of x. Then the way composition works is you take that new result and you plug it into the outer function, which in this case is f inverse. And what f inverse does is it basically undoes what function f did. And so the end result here, you're back exactly where you started with. So your end result here, ultimately your output here, is just your input here. So inverse function f inverse effectively undoes it undoes f. So normally we think of, addition and subtraction. Those two operations undo each other. Multiplication and division undo each other. So this idea of an inverse function sort of just generalizes what we know from addition and subtraction and multiplication and division. So a lot of the functions that we deal with have an inverse function. So for instance, sine, there's inverse sine. Tangent, there's inverse tangent. E to the x, there's natural log x. So a lot of the functions that we work with have inverse functions. And so there's also another cancellation property where if you do f inverse first and then you do function f, they still cancel out. So f inverse and f, they both cancel each other out. So one undoes the other essentially. And so f inverse, we just talked about this in the last example. The -1 here is not an exponent, so it's just notation. So when we write f with that -1 superscript there, it's all one piece of notation. So don't think of this -1 as an exponent. So when we see like f with that little -1 there, it's not an exponent. So it's not the same thing as 1 over f. So when we talk about the inverse function f with x plugged in, that's not necessarily the same thing as 1 over f of x. So it's just think of it as just some brand new function it just cancels off the original function. So let's see how we can use this definition and implicit differentiation to work out the derivatives of, I think we'll do inverse sine and inverse tangent. So let's do inverse sine first. So we're going to do the derivative of the inverse sine function. We're going to show that it's equal to 1 over the square root of 1 minus x squared. And so the first thing we're going to do is we're just going to start with our function, and we'll call it y, just to give it a name. So we'll call this y equals inverse sine of x. And so we're going to use our definition of inverse function, which said that y is equal to the inverse function evaluated at x. What that means is x is equal to the original function f evaluating y. So if y is equal to inverse sine of x, if we reverse it, what that tells us then is that x is equal to sine of y. And that's just the definition of the inverse function. So we have now our equation x equals sine of y, and this is where we do the differentiation. So we're going to work out the derivative over here. So here is where we're going to do our implicit differentiation. So let's write down our equation, and we're going to apply the derivative to both sides, just like we were doing before with implicit. And here we're treating x as a variable, and we're treating y as both a variable and a function. So on the left-hand side, when we differentiate x, we just differentiate it like usual. So derivative of x is just 1. And then on the right-hand side, we're going to do the derivative of sine of y. So we're treating y as both a variable and a function. So when we do the derivative of sine of y, we do the derivative like usual. So derivative of sine of y is cosine of y. But since we're differentiating a y term, we multiply that by y prime. So implicit differentiation gives us this new equation, 1 equal to cosine y times y prime. And that's it. We're done differentiating. Now all we need to do is to solve for y prime. And part of that means we have to convert back to x. So we're going to break this into 2 steps. Kind of working backwards now. And we want to convert back to x. So y prime is fine. We'll leave that as y prime. But we want to get rid of that cosine y term. We want to rewrite that back as an x. So there's a few ways to do this. One approach is to use these helpful trig identities. Sine squared plus cosine squared is equal to 1. Or if we had secants and tans, maybe secant squared is equal to 1 plus tangent squared. We're going to try a different approach, though. Still related. And it involves a right triangle. So let's, on our right triangle here, we're talking about, if we look at this equation, x equal to sine of y, we plug angles into trig functions. So sine of y means y is the angle. So on our right triangle there, we put y as one of the angles. And then in terms of a right triangle, sine is the opposite side over the hypotenuse. So we know sine of y is equal to x. So if we write x, that term on the left there, as a fraction, we could rewrite it as x over 1. And what that tells us then is on our right triangle, the side opposite angle y has length x. And then the hypotenuse of our right triangle has length 1. And then if we use the Pythagorean theorem to find the length of the missing side, we get square root 1 minus x squared. So we find that missing side by the Pythagorean theorem. Now, if we look at our equation from the implicit differentiation, we have cosine y. So we want to figure out what cosine y is. So we know cosine is the adjacent side over the hypotenuse. And so the adjacent side is square root 1 minus x squared, and then the hypotenuse has length 1. So this will be over 1. So we just fill that result into our equation. So that gives us 1 is equal to square root 1 minus x squared times y prime. And then the very last step here is we want to solve for y prime, just like we normally would do with implicit. And we're going to move that square root to the other side. So our last step here, solve for y prime. And when we do that, we get our result. Y prime is equal to 1 over the square root of 1 minus x squared. So it's this kind of subtle argument involving inverse functions, their definition, doing implicit differentiation like we did before, and then using a right triangle to convert our variable y back into variable x. All right, let's try another one of these. Let's look at inverse tan. We're going to do it very similar. And again, we're going to use right triangles, but another approach, you could potentially use the trig identity secant squared equal to 1 plus tangent squared. So that's another way to do it. But we're going to use right triangles again. So we start off, let's give our function a name. We're going to call it y. So y is equal to the inverse tangent function. And what we're going to do is we're going to apply the definition. So what does it mean to be an inverse function? Well, we know our definition says y is equal to the inverse function evaluated at x is the same thing as saying x is equal to the original function evaluated at y. So if y is equal to inverse tangent of x, that must mean x is equal to tangent of y. Another way to think of this is to just say, let's apply the tangent function to both sides. So tangent of y is equal to tangent of the inverse tangent of x. And then tangent and inverse tangent, they undo each other, so they really just cancel out. And we're left with just an x there. So x is equal to tangent y. That's just another way of thinking of inverse functions, is just through the cancellation property. All right, so once we have this x equal to tangent of y, we've gotten rid of the inverse function in our expression there. This is where we go on and do the implicit differentiation. All right, so what do we do? Well, we write down our expression, x equal to tangent y, and we're going to apply the derivative to each term on the left and apply the derivative to each term on the right. Derivative of x we're viewing just as a variable, so derivative of x is just 1. And then the derivative of tangent y, well, y we're treating as both a variable and a function. So derivative of tangent y would be secant squared y, but then because we're differentiating a y term, we multiply that result by y prime. So we get the equation 1 is equal to secant squared y times y prime, and we're done differentiating. All that's left to do now is to convert back to x and then eventually solve for y. All right, so let's see how we convert back to x. And we're going to do it again. We could use the trig identity there. Secant squared is equal to 1 plus tangent squared. But let's use a right triangle. So in our equation here, we have tangent of y. So that means y is an angle. So let's put y as one of the angles here. And then we know tangent is the adjacent side over the opposite side. And if we look at the other side of our equation here, it's equal to x. So let's write that as a fraction, and we'll write it as x over 1. So what that tells us then is on our right triangle, the adjacent side has length x, and the opposite side has length 1. And so then if we use the Pythagorean theorem to find the length of the hypotenuse, hold on, I think I wrote this wrong. Tangent is not, it's the other way around. So tangent y, we're talking about tangent, it's opposite over the adjacent side. So let's just check that out. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So when we do sine over cosine, we get opposite over adjacent. Yeah, a little typo there. So correction, if you were following along, and I see some people pointed it out there in the chat, it's opposite over adjacent. So let's just go through and correct that. Turns out that won't actually make too much of a difference. So opposite side is, so we still rewrite our x there on the left as a fraction, so x over 1, but it means the opposite side is x and the adjacent side is 1. That looks better. So then we use the Pythagorean theorem to find the length of the missing side, and it's 1 plus x squared, square root 1 plus x squared. All right, so we want to figure out what secant is, because we have a secant squared there. So secant is hypotenuse over the adjacent side. Give myself a little bit more room. So why is it that? Well, it's the reciprocal of cosine. So cosine is adjacent over hypotenuse. Secant is the reciprocal of cosine, so we just flip it. So it's hypotenuse over the adjacent side. And if we fill that in, hypotenuse we know is the square root of 1 plus x squared. And then the adjacent side is 1. So there is secant y. So let's fill that into our equation. So what do we get? We get 1 is equal to square root 1 plus x squared squared, because it was a secant squared there. And then we have times y prime. The secant, or the squared and the square root cancel. So really this just simplifies to just 1 equal to 1 plus x squared times y prime. And we want y prime by itself. So the last step there is to solve for y prime. So y prime is equal to 1 over 1 plus x squared. And we proved it. So again, it's kind of this process of step, the first part is just using the inverse function definition. Then the second part is using implicit differentiation. And then the rest of the work is just using what we know about trig functions, whether we use a right triangle or some other trig identity, to convert back to x. And then we finish solving for y. All right, so that's inverse trig functions, and there's other inverse trig functions, but the process you could do very similar. Now we're going to go on to exponential and log functions. And first we're going to use the chain rule to show the general result for just a regular exponential function b raised to the power x. And for this one, b is just a constant. So, when we think of e to the x, e is just a number. It's just a constant number. So here b, we're just thinking of it, it's just a number. And so how we're going to do this is we're going to use an important property of exponential functions or exponents. And we're going to use this property here that b raised to the power x is the same thing as e raised to the power x times natural log b. And why does this work? Well, there's log properties. There's properties of log that essentially allow us to take a number that's in front of a log function and we move it inside the log function and it becomes an exponent on what's ever inside the log function. So this is a log property that tells us this is equal to e raised to the natural log of b raised to the power x. So we take that x that's in front of the log and it moves inside the log, but now it becomes an exponent on the b term that was already there. And then e and natural log are inverse functions of each other, so they just cancel out. And what we're left with is b raised to the power x. So this checks out. This result checks out. So we're going to use that and chain rule to show this general derivative formula. So we're going to do the derivative of b raised to the power x. And let's rewrite it now with that property. So e raised to the x times natural log b. We're going to differentiate this. And really, this is a special case of the general exponential rule that we saw. And if we remember back to our chain rule, we saw a kind of a general case here where we had e raised to the kx. So some constant k times x. And what the general exponential rule said here when we were doing chain rule, you would keep the exponential part exactly the same, so e to the kx, and then you would take the term that's in the exponent and multiply by its derivative. So we have e to the kx times the derivative of kx, where k was a constant. So this was just a special case of the chain rule that we saw. So we're going to do the exact same thing up above. We keep our exponential function exactly the same, e raised to the x times natural log b, and then we multiply that result by the derivative of the term in the exponent. So x times natural log b. And when we look at this, natural log b is a number, b is a constant number, so natural log of b is also going to be a constant number. So when we do the derivative of a constant times x, the result is just the constant. So we end up with e raised to the x natural log b times x, or times natural log b. When we finish that differentiation, and then we know what this e raised to the x natural log b term is. Another way of writing that is just b raised to the power x. So we get b raised to the power x times natural log b. So, and that proves it. We use the chain rule to show that the derivative of just any old exponential function b raised to the power x is b raised to the power x times natural log b. All right, so we have now the kind of the general exponential derivative here. Now let's look at what happens with the general log derivative. So here we're going to use implicit differentiation to show that the derivative of log base b of x is equal to 1 over x times natural log b. And so we mentioned it before, log and exponential functions, they're inverses of each other. So in particular, when we say f of x equal to b to the power x and f inverse of x equal to log base b of x, these are inverse functions of each other. So it has to be the same base term. So b raised to the x and then log base b of x. Have to be the same number there, but they're inverses of each other. So we want to show that the derivative of this inverse function, and when we're going to do the derivative, when we're actually going to show the derivative of an inverse function, that's where the implicit comes in. So we're going to first write down, we'll give our log base b of x, we'll just give it a name, we'll call it y. And then we're going to use our definition of inverse function to just rewrite that. So we say y is equal to inverse of x. That's the same thing as saying x is equal to f of y. So if we use that definition, rewriting y equals log base b of x, we could write that as x equal to b raised to the power y. So we're just looking at this equation here, and we're plugging y into our exponential function. So that's how we get b raised to the power y on the right. All right, so we've used our definition now to kind of get rid of the inverse function in our expression. Now what we want to do is we want to actually do the derivative. So this is where the implicit comes in. So we're going to do our implicit differentiation next. Very similar process to what we were doing with the inverse trig functions. We're not going to have all of that right triangle business, though, that we had to with the trig functions. All right, so let's write down our equation. We're going to apply the derivative to both sides, just like we normally would with implicit. Derivative of x is 1. And then we just proved this. The derivative of b raised to the power y would be b raised to the power y times natural log b. But since we're doing the derivative of a term involving y, we multiply that result by y prime. So there we go. We're done with the differentiation part of it. And all that's left to do now is to convert back to x and then solve for y prime. So we're going to convert back to x. And the way we do that is just by noticing that here we have b raised to the power y, and we know that b raised to the power y is equal to x. So we just fill that in, and we get 1 is equal to x natural log b times y prime. And then we just finish solving for y prime. And we get y prime is equal to 1 over x natural log b. Just what we would expect. So it's kind of fun. These are, it really relies on a lot of techniques here in order to get these derivatives. But the process is kind of fun. We're using the definition of inverse function, some implicit differentiation, and then we're just converting back to x to get, and then solving for y prime. Now there's a special case of this, and that's what happens when the base b term is just e. So when this is the case, we could write log base e of x, but we don't normally write that. We give it a special name. We call it natural log, ln of x. And it's also helpful to remember that the natural log of the number e is equal to 1. So putting those together gives us our more usual when we talk about the derivative of a log function, this is the one we pretty much use the most in a calculus course. And that's because the derivative is fairly nice. But it's the one we expect. Derivative of natural log x is 1 over x. So that's just a special case of this derivative rule we just showed. Derivative of log base b of x is equal to 1 over x natural log b. All right, let's try one more just to kind of round out our process here of showing all of those elementary form derivatives. So here we're going to show that the derivative of the natural log of absolute value x is also equal to 1 over x. And as soon as we start seeing an absolute value sign, we have to think piecewise function. So the technique here is we're going to rewrite this natural log of absolute value x. We'll rewrite it as a piecewise function. And we know that absolute value behaves differently if x is greater than 0 versus if x is less than 0. And so if x is positive, if x is greater than 0, natural log of absolute value x would just be natural log x. The absolute value doesn't do anything. But if x was a negative number, we normally can't plug negative numbers into the natural log function. So what the absolute value effectively does is it says, all right, let's make it a double negative. So x is already negative. Let's throw another negative in front so that we get a positive out. And we just note here that natural log is undefined. Well, natural log by itself is undefined for negative numbers and 0. The absolute value is getting rid of the negative numbers, but it's still undefined at x equals 0. All right, so now we have this piecewise function, and we basically just go along and we differentiate each piece of our function. So let's look at the piece where x is greater than 0. Then when we talk about the derivative of natural log absolute value x, this is the same thing as just the derivative. If we look at that piece, it's just the same thing as the derivative of natural log x. So just fill in the actual piece of our function there. And we know from before, what we just did, derivative of natural log is 1 over x. All right, so that first piece, when x is greater than 0, that gives us our expected result. Now, if x is negative, if x is less than 0, well then we're going to do the derivative of the same function, natural log absolute value x. That's what we're interested in. But now we have to use that other piece of our function because x is negative here. And so we have we're going to do the derivative of the natural log of negative x. And so here, it's not just natural log x. There's some other stuff inside the parentheses there. So we have to use the chain rule. So how does the chain rule work for a log function? Well, you do the reciprocal of what's in the parentheses, so 1 over negative x, and then you multiply by the derivative of what's inside the parentheses. So derivative of negative x. And then if we keep differentiating, derivative of negative x is negative 1. And then the negatives, the two negatives end up canceling, and we're just left with 1 over x. So that gives us it gives us the same result here for both of these. So putting those together shows that derivative of the absolute value of the natural log of the absolute value of x is also 1 over x. All right, so that'll stop with learning outcome D5 here. And so I'm seeing a question in the chat. So for this learning outcome, when we go back to our elementary forms here, most likely you just want to have these memorized. But for this specific learning outcome, I do want to see that you can actually go through kind of the steps here for either proving proving these derivative rules. So when you're for the homework, you're going to see the process is kind of laid out in the homework, and then on the exam, I'll expect you to I'll basically, it'll be a question like this: use implicit differentiation to show blah blah blah, or use the quotient rule to show blah blah blah, something like that. So for this particular learning outcome, I do want to see all of the steps here, but in practice, once we and as we've really have seen, I do just expect you to have these memorized. So you probably have them memorized, but I do want to see that you can kind of go through at least one of these arguments. All right. So let's go on to learning outcome D6. And this is really just, part of it's just review. So just being able to take all of the different derivative rules that we've used and just be able to use a bunch of those rules together. And that's really all this is. So there's a little bit new here that we're going to talk about, but a lot of it is just techniques, putting all the techniques together. So let's try this first one. We're going to calculate the derivative of the function y equal to x times arctan of square root x. When we look at this function, there's a few things going on. But really the major thing here is right there in the middle, there's a multiplication sign. So there's x times arctan of square root x. So there's multiplication in between two functions of x. So we're going to use product rule here. That's the very first thing we have to do for this, calculating this derivative. So there's a product right there in the middle. We have to use product rule. All right, so how do we implement the product rule? Well, we just write down two copies of our function. And instead of square root x, I'm going to rewrite that as x raised to the 1/2. So we just write down two copies of our function there. And then in the first copy, we differentiate the first term. In the second copy, we differentiate the second term. And we put a plus sign there in the middle. So that's product rule. Then we keep going. We differentiate. So derivative of x is 1. And we don't normally write 1, so I won't write it. And then we have the arctan of x raised to the 1/2 power. That's outside the brackets, so we don't differentiate it. Then we have plus x. That's outside the brackets, so we don't have to differentiate it. And then all that's left to differentiate is that arctan of square root x term. And so here we have an inverse trig function with a square root function plugged into it. So it's a composition. So we have to use the chain rule here. So in this example, we have to do both the product rule and a chain rule in order to ultimately get the derivative. So what's the derivative of arctan? Well, we go to our table here, and it's 1 over 1 plus whatever was plugged in squared. So we'll write this as 1 over 1 plus blank squared. And then let's fill in what that inner function was. It was x raised to the 1/2 power. And so that's the derivative of the arctan part, the outer function. We have to then multiply that by the derivative of what was inside of it. So the derivative of x raised to the 1/2. So derivative of arctan gives us that fraction. Derivative of the outer function gives us that fraction. And then we're multiplying by the derivative of the inner function. And then we just keep going. That first term we're done with. The x raised to the 1/2 power, which is then squared, the squared and the 1/2 cancel out. So we're just left with an x there. And then we multiply by the derivative of x to the 1/2. So that's just power rule. So 1/2 x to the negative 1/2. And, we could go a little bit further to rewrite that, but that's fine. We'll stop there. So part of this learning outcome is just really going to be just applying multiple rules. So for this one, we had to do product rule, then we had to do chain rule. Let's try another example also with product rule and chain rule. So we're going to look at the function 2x plus 1 all raised to the power 5 times x cubed minus x plus 1 all raised to the power 4. And when we look at this, there's multiplication right there in the middle. So there's some x terms on the left, there's some x terms on the right. We have to use product rule. All right, so let's do it. So we write down 2 copies of our product. So 2x plus 1 to the power 5 times x cubed minus x plus 1 raised to the power 4. Same thing on the left. We write down a second copy, and we put a plus sign in the middle. In the first copy, we apply the derivative to the first function. In the second copy, we apply the derivative to the second function. And then we're going to keep going. So when we look at this, we did our product rule. Now we have to differentiate each of those terms inside the brackets. And for each of those, we have to use our general power rule. So chain rule. We have to use the general power here, and we have to use the general power rule over here. So we keep going, keep differentiating. So the derivative of that 2x plus 1 to the power 5, we bring down the 5. Keep what's inside the parentheses exactly the same. Subtract 1 from the exponent, so that brings us to 4. Then we take the result we take the term that's inside the parentheses, and we multiply by its derivative. So that's the general power rule for that first portion. Then we have x cubed minus x plus 1 raised to the power 4. That's outside the brackets, so we're done with that. Then we have plus. Then we have 2x plus 1 raised to the power 5, also outside the brackets, so we're done with that. And then we're going to do the general power rule again for that other power function. So we bring down the 4, put it in front, keep what's inside the parentheses exactly the same, subtract 1 in the exponent, which takes us down to 3, and then take the term that's inside the parentheses and multiply by its derivative. So that's also just the general power rule. And then we keep going. So we're done with that 5 times 2x plus 1 to the 4th. Derivative of 2x plus 1 is just 2. And then we're done with this other term here. And we're done with this. And we just keep going, differentiating only what's in the brackets. So we finally get to that derivative of x cubed minus x plus 1, and the derivative there is 3x squared minus 1. And we're done. So that's the derivative. Now, you know, it's normally helpful to try and simplify the derivative down. So we won't go through it, but what you would want to do is you can factor. So if we look, there's kind of two pieces of our function here. There's this first part, and then there's the second part. Both parts of our function there have a 2x plus 1 in it. So we could actually factor out a 2x plus 1 raised to the power 4 from both of those. And then we also see both of them have an x cubed minus x plus 1. So there's 4 copies in the first term. There's 3 copies in the second term. So we could actually factor out an x cubed minus x plus 1 cubed. So you could factor out each of those in order to help you kind of simplify this derivative down. We won't go through that, though. All right, let's try another example of just doing multiple derivative rules. So we just want to really practice these. This is really what it comes down to. Just the more practice we get doing derivatives, you know, the better off we'll be going later into the course. So let's look at this one. We have this function g of t is equal to t minus 2 divided by 2t plus 1, all raised to the power 9. And when we look at this, the very last thing that's happening to this function is that raised to the power 9. So what we start with is the general power rule, chain rule. So how does the general power rule work? Well, we bring down the exponent, 9. Keep what's inside the parentheses exactly the same. Subtract 1 from the exponent, so it takes us down to 8. And then we take the term that's inside the parentheses and we multiply by its derivative. So we want to do the derivative of t minus 2 divided by 2t plus 1. So we did the chain rule. Now, when we look at that, the remaining derivative that we have to do is a fraction, and there's variables on both the top and the bottom. So the next derivative rule that we're going to use is the quotient rule. So the 9 times t minus 2 over 2t plus 1 raised to the power 8. We're done with that, so that no more work is going to happen there. And now we just need to apply the quotient rule to that fraction. So the way we implement the quotient rule is top times bottom. And be careful, I'm guilty of it. With t's, my t's start looking like plus signs. So when you're doing these, if your variable is t, just make sure you're careful so that your t's look like t's and your plus signs look like plus signs. So we're going through implementing the quotient rule. So we write down top times bottom, 2 copies, similar to product rule. And then we put a minus sign now in the middle. And then in the first copy, we apply the derivative to the first function. And then in the second copy, we apply the derivative to the second function. And then all of this is over the original denominator squared. So 2t plus 1 squared. All right, so that's the quotient rule. We still have a few more terms to differentiate, but each step along the way here, the terms that we have left to differentiate are getting simpler and simpler. And so now we get it to a point now where t minus 2, we can just do that derivative. 2t plus 1, we can just do that derivative. So again, the 9 and that t minus 2 over 2t plus 1 raised to the power 8, we're done with the derivative there. Derivative of t minus 2 is just 1. So I won't write the 1. So it'll just be 2t plus 1 minus t minus 2. And then the derivative of 2t plus 1, that remaining bracket, is 2. And this is all over the denominator, 2t plus 1, and we square it. And we don't multiply that out. Normally with quotient rule, we don't do anything to the denominator. We just leave it as the denominator squared. So that's it. We're done differentiating. But with quotient rule, sometimes you can simplify what's in the numerator. So really that's what we could do next, is we could just take the term that's in the numerator here and just simplify it down a little bit. So not much to do here. So if we do the simplifying, we would end up with 5, all in the numerator. So sometimes it's helpful, if you can, to, once you have the derivative, try to simplify it. And especially when you're typing these answers into WebWork, if you can do the simplifying by hand, a lot of times there'll be less things for you to actually type in. So just a little helpful tip there. All right. Let's look at one more. We're going to do the derivative of this function, which is the natural log of x plus 1 over the square root of x minus 2. And so when we look at this, we see that the very last thing we do is a log function. So we would have to use the general logarithmic rule. Really just a special case of the chain rule again. So what does that rule say? Well, when we differentiate the log function, it kind of does the reciprocal of what's inside the parentheses. So the derivative of our outer function here would be 1 over x plus 1 divided by the square root of x minus 2. And then we take the term that was inside the parentheses and we multiply by its derivative. And as we look at this, it's a fraction. So there's a few things we're going to have to end up doing. We're going to have to use the quotient rule. It's a fraction. There's variables on both the top and the bottom. And then when we look at the denominator, it's a square root of x minus 2. So we would have to use our general power rule for whenever we differentiate that term. And so there's kind of 3 different derivative rules that are going to come into play here. The general log rule, which is really just a special case of the chain rule. Then when we get to the inner function, we're going to have to use the quotient rule, and then we'll also have to use the general power rule. So it's going to be quite involved to do it this way. And it's perfectly fine if you want to do it this way. So we're going to stop there on this one. And we're going to look at the natural log function a little bit more. So it's perfectly fine if you want to, it's kind of like a brute force attempt where you're just kind of going through the derivative rules, and you can do it perfectly fine. But instead, we're going to consider some properties of the natural log function, which are going to make the differentiation process quite a bit easier here. So there's 3 main properties, and you probably have seen these before. So if we have 2 numbers, x and y, and then some other number b, The first property here says that the natural log of x times y is the same thing. It's equal to the natural log of x plus the natural log of y. So what we can think of this rule as saying is if we have multiplication inside our log function, it takes that multiplication inside our log function and it converts it into addition outside of the log function. Then the second property, it has a fraction there. So what the second property says essentially is the log function converts division that occurs inside the log function into subtraction outside the log function. So that property says if we have the natural log of x divided by y, that's the same thing as the natural log of x minus the natural log of y. And just to note, I have these properties listed for natural log, but they also work for just any log function, log base b. So it's true for any log function. And then the last property says if we have the natural log of x raised to the power b, well, we can bring that exponent and we can put it in front of the natural log. So this one tells us how to handle where we have, exponents, multiple exponents. And so if you're looking at this, there's no property. So just a note here. No rule to simplify natural log of x plus y. So if the addition occurs inside the natural log function, we're kind of just stuck. There's no rule to simplify that further. Same thing with subtraction. If subtraction occurs inside the log function, we're kind of just stuck with it. But if it's multiplication, division, or exponents, we can do quite a bit of simplifying there. Also, it's worth mentioning each of these sort of has an analog in terms of exponential rules. So let's just remember some of the exponent rules. So if we have e to the x times e to the y, so if we have multiplication of exponential functions, that's the same thing as adding the exponents together. If we have division, so e to the x divided by e to the y, that's the same thing as if we were to just subtract the exponents. So e to the x minus y. And then if we were to have e to the x all raised to the power b, well, that's the same thing as if we were to just multiply the exponents together. So each of these log properties has a very similar property for when we talk about the exponential function. All right, so let's see how these are useful. So we're going to look at this derivative again, this function again, the natural log of x plus 1 over the square root of x minus 2. But now we're going to think of it in terms of these natural log properties. So what we're going to do is we're going to start by, rather than just starting the derivative right away, we're going to simplify this natural log expression first. So let's see how this would look. So we have a fraction, top x plus 1 on the top, and then the square root of x minus 2 on the bottom there. So we could write this as, if we use that second property, tells us what happens when we have a fraction. It says we do the natural log of the top function, and then we subtract, and then we do the natural log of the bottom function. And then instead of writing that square root sign, we're going to be doing derivative. So let's rewrite that as an actual exponent there. So that's using property B. Now we can actually go a little bit further. So we have this raised to the power 1/2 that's really inside this second natural log function that we have. And so we have another property that tells us what to do when we have an exponent like that. And what we can do is we can take that exponent and we can bring it out front. So we can bring that 1/2 and put it in front of the natural log here. So the first natural log we're done with, and then we're just going to rewrite that second one as negative 1/2 times the natural log of x minus 2. Now it feels like we've done a bunch of things, and we have, but we haven't done the derivative yet. So you don't want to stop here. We actually have to do the derivative. But in terms of simplifying, this is as good as we can get it. So now we go on and we calculate the derivative. So the derivative of that first natural log, what does it do? Well, you just do the reciprocal, and then you multiply by the derivative of what's inside the parentheses. Then we have a minus 1/2. And then the derivative of that second natural log term is 1 over, it's the reciprocal, so 1 over x minus 2 times the derivative of what's inside the parentheses there. And then if we go a little bit further, derivative of x plus 1 is 1. So we just get 1 over x plus 1 as the first part. Then we have minus 1/2 times 1 over x minus 2. And the derivative of x minus 2 is also 1. So there's our derivative. We're done differentiating. And notice that we didn't really have to do the quotient rule, and we didn't have to use the general power rule at all. So using those properties of natural log kind of simplified the differentiation process down quite a bit. All right. Let's see how we can use those properties. And we can kind of develop just a general differentiation technique for some of these more complicated looking expressions. So we call this new technique logarithmic differentiation. And it's really just probably easier to think of it as a process. So we're gonna go through this example to see how this will work. So this is the same function that we differentiated before, but one of the earlier examples where we had to use product rule and then general power rule a few times. But what we're going to do here is with this technique of logarithmic differentiation. And we're really going to utilize those log properties to simplify down the process. So first step, we apply the natural log function to both sides of our equation. Very first step, that's how this technique works. We apply the natural log function to both sides. Not much is going to happen on the left, but on the right, now we have a log there, and we have a product, we have some exponents, so now we can go through all of the simplifying that we're used to in terms of those log properties. And that's step 2. Not much happens on the left, but on the right, we have a product, so we could split this up into the sum of two log functions. And then those exponents that we have, and you know what, I'll do that in the next step. So we have those exponents. So first we split up the multiplication into the sum of two separate log functions. Then we have exponents, so we can bring those exponents out in front of the log function. So we could write it as 5 times the natural log of 2x plus 1 plus 4 times the natural log of x cubed minus x plus 1. And that's the simplifying the right-hand side as much as we can. Then we go on and do implicit differentiation. So implicit differentiation comes back again, rears its head again. Let's do the right-hand side first. So 5 is a constant. Derivative of the natural log 2x plus 1 is 1 over 2x plus 1 times the derivative of what's inside. And I apologize, we're going to go over for like a minute or two here. Then we have plus 4. And then the derivative of natural log x cubed minus x plus 1. We're doing implicit differentiation, but really it's all x's on the right here. So it's just usual differentiation on the right. So derivative of that natural log x cubed minus x plus 1 is the reciprocal times the derivative of the term in the inside the parentheses. And where implicit differentiation really comes in is what happens on the left-hand side. So that's where we differentiate the natural log of y. So we have a y term there on the left, so we differentiate it like usual. We get 1 over y, but because it's a y term, we multiply the result by y prime. And that's really the only really noticeable use of implicit differentiation there, is just when we're differentiating that natural log y. All right, so then we keep differentiating if we have any brackets to finish up. So derivative of 2x plus 1 is 2. So I would write that as, I'd multiply it with the 5 and put it all over that fraction 2x plus 1. Then we have the 4. And the derivative of x cubed minus x plus 1 is 3x squared minus 1. So I would put that all in the fraction for, all in the numerator for that second fraction. And so this would be over x cubed minus x plus 1. So if we just clean up the right-hand side there, we get 10 over 2x plus 1 plus 4 times 3x squared minus 1 over x cubed minus x plus 1. Now the last part of this, step 4, is we want y prime by itself. So what we're going to do to get rid of that 1 over y, we're going to multiply both sides of our equation here by y. And so that'll cancel it off on the left there. So that'll give us y prime by itself. And then the very last thing we do is we fill in what y actually is. So we know what y actually is from our original equation. So it's 2x plus 1 raised to the power 5, x cubed minus x plus 1 raised to the power 4, and then we have everything else. So 10 over 2x plus 1 plus 4, 3x squared minus 1 over x cubed minus x plus 1. And there it is. There's our derivative. And it's kind of nice doing it this way because it almost gives you a factored version right away. So we did it kind of just the brute force method of doing product rule, doing chain rule. Perfectly fine to do it that way. Here is with the technique of logarithmic differentiation, and you kind of get, more of a factored version, which might be helpful. So just another way to do that derivative. All right, so we'll stop there for today. We'll pick up with we'll look at a few more logarithmic differentiation problems next time. But I just wanted to finish that one for this time, so I apologize for going over a few minutes there. Next week is our third recitation exam, so make sure you look at your results on Gradescope and see which questions on exam 2 that you didn't get correct. Those are the ones you're going to be making up on the follow-up exam portion. So just make sure you have those, you know which ones you need to do. And then go through the lecture and see, look at the examples that we did in lecture to see what we're looking for on those problems that you missed. So, a big one that I'm seeing is with limits. When we talk about the limit of a function, part of it is being able to use the notation correctly. So I want to see that you're using the limit notation correctly. You know when to plug in, to evaluate the limit, that sort of thing. So it's all part of it here. So if it's a limit problem that you're making up, make sure you're using the limit notation. So that's probably been the biggest issue that I've seen so far in grading these, is just the use of that notation. All right. So we'll stop there. Have a good weekend, and then we'll see everyone next week for lecture and recitation. Bye-bye.